Hey everybody, welcome back. We're looking at Stokes' theorem in Calculus 3. This is our last section, 15.8. We're working on examples. Recall Stokes' theorem is f dot dr, the line integral for f dot dr, which is work in physics, around a curve. A closed curve is the same as the surface integral of the curl of f dotted with n for that surface. We've been using the surface integral to find the line integral. So calculating the right side to figure out the left side. It does work both ways. If the surface integral is really ugly and you can't find a simple one that works, sometimes doing the line integral will get it for you. Usually you're not having that curl of f dotted with dn, but let's just look at doing a problem with both ways on the next example. So for this example, we're going to use Stokes' theorem to find the curl of f dot n ds, where f has xz in the I direction, yz in the j direction, and xy in the k direction. And s is the sphere of radius 2 that is inside the cylinder x squared plus y squared equals 1 and above z equals 0. So I tried drawing my cylinder here and then a sphere that intersected it. It looks crappy. This is what the top looks like without the XY axis on it. A little bit cleaner there. You can see I've got GeoGebra running in the background. I was trying to load this there. It's giving me the big FU. So just bear with me here. We've got this surface up here, and we're looking at that mound right there that's just above where the cylinder intersects it, because the cylinder keeps going. Cylinder doesn't stop there, it keeps going, but that's where the cylinder and the sphere intersect. Notice we've got n going, no matter, depending on where we're at, n is going in a different direction. So let's take a look at doing the line integral first. We can find the curve C by finding where the sphere and the integral intersect. So the cylinder was x squared plus y squared equals 1. The sphere is x squared plus y squared plus z squared equals 4. That's a sphere of radius 2. And what I did here is I took x squared plus y squared. I know that equals 1 where they meet. And so I replaced that there, right there. I've got 1 plus z squared equals 4, so z equals square root of 3. The other option is setting these both equal to 0 by gathering everything on the same side. And if they're all gathered on the same side and they both equal 0, then these two things have to equal each other since they both equal 0, and then solving for z there. Depending on how you like to do it, that'll get you the same thing. But what we end up with is this curve going around here at z equals square root of 3. We are doing, it looks like a circle, so we can use x equals r cosine t and y equals r sine t. For this specific example, r is 1. So this just simplifies to cosine t and sine t. Make sure you memorize it with the r. I've seen on tests, people don't have the r memorized. They're just doing x equals cosine t. That doesn't work. It only works for unit circles, which this happens to be one. So we've got z equals square root of 3. We're going to use this stuff right here. Let's take a look at it. So if I write r, we're doing f dot dr. I got to make r. So r is cosine t for x, sine t for y, and square root of 3 for z. So r prime of t will be negative sine t, cosine t, and 0. So I am going to evaluate f of r dot dr in the integral. So if I plug in r into my function, recall f was xz, yz, xy. So the z is the square roots of 3. That's right there. I have the x right there, the y right there, and then xy is that right there. So that's where I got those components. I'm dotting that with r prime of t, which is this right here, dr dt. And you see we get this negative square root of 3 cosine t sine t plus square root of 3 sine t cosine t equals 0. That all adds up to the integral of 0, so the total is 0. Let's look at doing it the other way. Now, recall we had a pipe, and the surface was at the top. It was this part right there. Well, I still made it look crappy. And so in the red part, it's this value right there. It's that surface. And so n has got different values depending on which way it's going. Let's take a look at doing it. It is important to know, though, recall that I said, remember the bubble example I gave you? Use the simplest surface that has the same closed boundary. The shitty surface, the real surface, had n going in different directions. I can just use the disk. This was x squared plus y squared equals 1. So it's a circle of radius 1. And it was a flat plane. That was at z equals square root of 3. It's a flat plane. So n is 0, 0, 1 right there. If I do the curl of f, again, f was xz, yz, and xy. We do the curl. We've got x minus y for the I hat, x minus y for the j hat, and 0 for k. We dot that with 0, 0, 1, which is our normal for this disk right here. Not the actual surface, but the disk that has the same closed boundary. The dot product is 0, so we're integrating 0, and again, we get 0 as the answer. This took advantage of a simpler surface. Not always do you get a simpler surface, but this was a perfect example where we did. That's it for this video. We're going to talk about circulation in the next video. Peace.